Coming back to the slides, the value of the critical temperature for the 2D Ising model can be calculated exactly, and the value of J by kBTC is half ln of 1 plus root 2. Okay. But in our case, we have set J equal to 1 and we are measuring temperature in units of J. So, in that case, we putting J equal to 1, the value of kBTC will be exactly this factor, and it is 2 by ln of 1 by root 2, and when you put in the numbers, the value comes out to be 2.27 when J equal to 1. And that is exactly what we saw, right. The peak in the CV and the high was in this range. It was below 3, but above 2.2 definitely, and of course, the peak was shifting. The problem remains, since the position of the peak was shifting continuously, how do we calculate the value of Tc? Right. For the 2D Ising model, of course, it can be calculated exactly. We are implementing the 2D Ising model on the computer because we can exactly check, but for the 3D Ising model, as of date, nobody can calculate the value of the critical temperature accurately. By the way, just let me tell you that by computer simulations and also by analytical techniques which are approximate, you can be accurate only up to a certain degree. The value of the J by kBTC for the 3D Ising model is known, and its value is 0.2216, right. And if you set J equal to 1, if you measure temperature in units of J, which is what we have been doing till now, then the value of kBTC comes out to be 4.51, is basically 1 by this number, right. Just for the sake of completeness, I think I have said this before, that in the 1D Ising model, so when all the spins are placed along a line, so that each spin has just 2 neighbors, so on the 2 sides, and this was proposed by Ising sometime in the 1920s, and Ising did not find any phase transition. What does it mean? It means that as soon as there is any finite value of temperature, the tiniest value T going very close to 0, right. As soon as there is a finite value of the temperature, there is no order in the system, that is that the average magnetization goes to 0, right. So, there is no transition. Only at T equal to 0 do you find that all spins are either pointing up or down, but at any finite temperature, and it can be calculated easily for the 1D case. He found that the transition is 0, so he gave up. He thought that the model is of no use, and it took for quite a few years, 20-25 years, before Onsager could calculate it exactly, could analyze the Ising model exactly in the 2D case for the 2D Ising model, and he used some transfer matrix formalism, which you should read up in your statistical mechanics book if you are interested in the topic. And there he found that yes, at any finite temperature, there is an ordered state, there is a large number of spins pointing in the same direction, so say the positive direction, and only when a temperature is raised above a certain critical temperature do you get disorder. In the 1D, at any small finite temperature you will getting disorder. In 2D, you are getting disorder only when the temperature is raised above a certain value, right. And of course, different systems would have different values of J. I mean, or what you could do, that if a system is has interacting spins, which in the Ising case you find out the Tc and back calculate the J, that is also possible, and for 3D of course, it is a even higher value in terms of J. The problem remains that for suppose the 2D or the 3D case, and suppose you did not know the TC, then how would you figure out or how would you calculate the exact value of TC, especially since there has been significant finite size effects. The value of the TC, the value of the peak in the CV and the chi were shifting to the left as you went higher and higher box sizes, larger and larger box sizes. The way you do it is by calculating the so called Binder's cumulant, and where it comes from and so on and so forth is out of the scope of this course. One needs some more statistical physics, some scaling theory, some finite size scaling analysis to understand from where this Binder's cumulant comes from. Here I shall simply tell you the method how to identify the exact critical point. So, what one has to do is calculate the Binder's cumulant, which is 1 minus m to the power 4 expectation value by 3 m square expectation value. At each microstate state, calculate the value of m square, calculate the expectation value and then take a whole square. And note that here I have written basically a subscript L here and a subscript L here. So, for different box sizes, for different lattice sizes, you can calculate M4 average, calculate M square average, square it, calculate this quantity, entire quantity, and this is called U of L or the Binder's cumulant. Now, you can calculate this quantity for different box sizes, different values of L. And at TC, the values of the Binder cumulant is exactly the same independent of the box size. As I said before, where and why this happens, we are not discussing this, that is outside the scope of the course. But what you could do is calculate UL versus the temperature for different box sizes near the critical point. So, basically suppose this blue line and the green line and the dashed line, they are for different box sizes. You are calculating U of L near the critical temperature and plotting it as a function of temperature. These different lines are box sizes, and at the critical temperature all the lines will intersect. So, the point of intersection is essentially the critical temperature. Now, let me tell you, I mean you are supposed to do it for your homework, but let me tell you that to calculate the critical temperature exactly, one has to do it iteratively, which means like you already know from the data that you have seen that basically the critical temperature lies between 2.2 and 2.3. So, take different values of dt, small values of dt, change the temperature from 2.2 to 2.3, calculate U of L, plot it as a function of temperature for different box sizes, and what you will see is the different lines nearly seem to intersect at a point, but not exactly. But once you identify the approximate range of the temperature where it is approximately intersecting, now again run the simulations for even smaller values of temperature over a smaller temperature range nearer the critical temperature, and if you do it iteratively, you will come across a temperature, you will come across a point, a value of T where all the lines intersect, and that is your critical temperature, and that is what it means by doing it iteratively. If you want to know more about it, the details, the background theory and much better analysis has been discussed very well by none other than Kurt Binder, on whom the Binder's cumulant is named. So, there is a book by Kurt Binder and Dieter D. W. Hermann, Hermann, and the book is called Monte Carlo Methods in Statistical Physics. If you want to know Monte Carlo methods in statistical physics in greater detail, there is also a book by Kurt Binder and D. P. Landau, and it is called Monte Carlo Simulations. This is a quite an advanced book. It really discusses all the advanced techniques. If you are learning Monte Carlo simulations, I would advise you to refer to this book. If you are already an expert and want to know advanced techniques, then this is the method. in this course the aim is not to make you an expert in Monte Carlo, but basically expose different types of computational methods to you, so that whether you do stat mech or you do space science or gravity or whatever be material science, you develop the skill set to go into that research area, do the calculations, implement the code and test it out. So, our aim is not to have a great or detailed understanding of Monte Carlo simulations or physics of phase transitions. This is just an exposure, just to let you know. So, we will be stopping within the next 10 minutes, but if you wanted to know more, there is the entire phenomena of finite size scaling, there is the scaling laws, there is this critical phenomena. So, even in the Ising model, as you go close to the critical temperature, various quantities such as the magnetization, the CV, the correlation length, they show certain scaling laws, and that is within the realm of critical phenomena. So, unless you know more about statistical physics and critical phenomena, it would not be relevant to discuss those points in detail, but the point I am trying to make is I just gave you a brief exposure to Ising model simulations, just to have an idea how to model things on a lattice, find out its properties, implement boundary conditions and so on so forth. Just to let you know, in our current simulations, the ones which I showed you, we were calculating we were collecting data to calculate thermodynamic averages, average E, average M, every Monte Carlo step, right. Every Monte Carlo step we were calculating it. That is a bit of a overkill. One should basically take thermodynamic averages over microstates which are not linked, which are statistically independent of the previous microstate. In one Monte Carlo simulation, it is not necessary that you will get a independent microstate. That is particularly true at lower temperatures, and here I want to mention that to do it properly, to figure out whether you are getting independent microstates at the end of every Monte Carlo iteration, one Monte Carlo step, one has to calculate the so called relaxation time, and the relaxation time specially goes as L square, L to the power x, where x equal to 2 for a 2-dimensional lattice. And what one should ideally do is take this data after a few MCS, and it really depends whether the check, and it is really important to check whether these microstates over which you are collecting data to calculate thermodynamic averages are statistically independent or not. So, we shall end this module with a last point, which is basically discussing the principle of detail balance. Till now, I have been, when I have been discussing the algorithm, I have been basically telling you that to implement the Metropolis algorithm in an importance sampling way, what you should do is flip give a trial flip to a spin selected randomly. If due to this flip the energy of the system locally over the spin and the system decreases, accept the trial flip. However, if due to the trial flip the energy of the system increases, then accept it with probability e to the power delta E by kBt. Now, you have been asked to simply accept that, but where does this algorithm which I basically dictated to you come from? And that comes from the principle of detail balance, it comes from statistical physics. Now, what is the principle of detail balance? So, for that we have to discuss the so called Master's equation. In Master's equation is an extremely generic equation. Now, suppose that you have set of states. Okay, so 1, 2, 3, 4, so on so forth, and in general call one of the states, these are energy states, to be I. Okay. And suppose that in each of these energy states there is a certain number of particles. Later we will change the language from particles to microstates, but for the simplicity just we will make that analogy later. But suppose there are some discrete energy states 1, 2, 3, 4 with energies E1, E2, E3, E4, EI, EI plus 1 and EI plus 2 and so on so forth, and each has a population, a number of particles if you like, N1, N2, N3, N4, Ni, and then higher states is Ni plus 1. Okay. And due to some physics, background physics, suppose the number of particles in each state, in suppose state I, which let us focus on that on the energy state I, that can change. How can it change? Because particles will jump from I to suppose energy state 3 or 2 or 1 or I plus 2, so on so forth. And so basically from here particles are jumping to different energy states, and similarly from other energy states there are particles which are jumping into state I. In that case, one can write in the most general manner the so called Master's equation, which says d n I dt, the number of change in the population of state I as a function of time, that depends upon p k I. So, the probability of hopping from state k to state I, from state k to state I, and the population of state k. So, suppose k will be 1, 2, 3, 4, I plus 2, I plus 1, all states except I, sum over k, k goes over all the states, and this comes with a positive number because from different states particles are hopping into state I. So, transition from k to I, population of n k, right. So, it will depend upon this transition probability into population density of state k minus. So, from state I there is a certain transition probability for a number of particles to go to state 3, 2, 1 and so on so forth. In general from I to k, the transition probability I to k into number of particles in state I, and this comes with a minus sign because as particles hop they transition from state I to other states, other energy states, the population density of I decreases, hence there is a negative sign here, right. And this equation will always be true. In general p k I could also be a function of time, but if it is not, if one has a so called stationary state, in that the population densities in each of these states are not changing as a function of time. So, d n I dt equal to 0 say, so that would be a stationary state, and that can happen in two ways. Now, let us focus on state I, right, and that can happen if the sum is 0 as a whole. Alternatively, if each of these terms in the bracket are 0. So, basically this quantity is 0 for each term individually, right, and then also you could have d n I dt equal to 0, which is a stationary state. Now, if there was a current from any pair of state, so that only the sum of the sum which was on the right hand side of the equation is 0. The sum is 0, then also you can have d n I dt, then you what to have is a steady state. Basically, there is a net flux of particles from one state to the other, I to I plus 1, or negative current if there is from particles going from 2 to I and so on so forth, and that is when you have a steady state. On the other hand, if each term in the bracket this term is equal to 0, that is a condition for equilibrium. So, individually for any pair of states I and k, if this condition holds, that is a condition for equilibrium. Now, with this background, we know that we are looking we were looking at Ising model in equilibrium, right. Now, think that these energy states that I was talking about, those are the various energy states that the Ising model can access, and at a particular value of energy corresponds to a certain number of microstates. Different microstates can have the same energy, right. So, just think that these NIs are not particles, but the number of microstates which are accessed at energy I 3, 2, 1 and so on and so forth, energy I, E2, E3, E1, right. For equilibrium, this relation holds, and that relation holds for every energy state, pair of energy states I and k. Now, we also know that the number of microstates which will be accessed. So, basically Ni will be e to the power minus beta Ei by z, and k will be e to the power minus beta Ek by z. So, higher energy microstates are accepted with or accessed with lower probability. Basically normalizing constant is z, and in that case we can write this to be, we can rearrange this, put in the expressions of Ni and Nk, and we can write it. So, here there is a mistake, there has been a mistake. So, now I have corrected it, and then this comes to be e to the power minus beta Ei minus Ek. It is something like the Boltzmann factor. Of course, the Boltzmann factor has to come here, and then one can write Pki equal to Pik into e to the power minus beta Ei by Ek. Now, suppose the particular k I am talking about is such that I is higher than k, which means Ei has a higher value than Ek, right. And if we set Pik equal to 1, then Pki automatically becomes. So, basically if we fix this value, okay, so there are two unknowns here. So, if we fix this value, we immediately, the value of this is fixed, we can fix it to be 0.5 or 0.25 or 10, and then immediately the value of this gets fixed. Here we have said let Pik equal to 1, and then Pki automatically gets fixed at this value, which means that if I was at a higher energy, if you basically say that if a microstate is being accessed k, which is of lower energy than I, accept the transition, accept the spin flip with probability 1, then between k and I, the probability of accessing from going from k to I is this, and that is exactly what we have implemented in our simulations, and this relation holds for every pair of i's and k's, right. So, if it is going, if this value is more, I mean, so even if it was I plus 1 and k, then basically you can again choose this, that to be 1, right, Pi plus 1 to k to be 1, and then the probability of Pk to I plus 1 would suitably be affected, right. So, this is where the Metropolis algorithm comes from, and this is the background physics. It is extremely important to know where the Metropolis algorithm comes from. I intentionally discussed it at the end, so that you understood the algorithm, and then I would tell you the physics. With this, I come to the end of this module, and from the next class we will be discussing differential equations. Thank you.